So today's talk is going to be on the automatic construction of inlining heuristics using machine learning. I know that a lot of people have done method inlining and inlining heuristics, and my talk is primarily going to be to explain that there is still further improvement that you can do and get some more performance out of inlining heuristics and tuning them. So this talk was done, this work was done primarily in Oracle Labs and at the University of Delaware. The authors of the paper are Professor John Cavazos, Christian Weimer, and Doug Simon. So the outline of the talk is primarily going to be a very short introduction of what is method inlining, what are the present inlining mechanisms, what are the possible solutions that you can have, our proposed solution, and what are the results and the conclusion. So in its briefest, method inlining is basically trying to embed one method into the body of another method. As you can imagine, the obvious advantage is the fact that it saves context switching time. The other secondary advantage is that it enables you to have other compiler optimizations because you've got a bigger code to work with. A disadvantage is that it increases the memory footprint, and that could actually hamper the performance of the application. It's a classic knapsack problem, but is it really important? So to motivate this particular work, what we tried to do was try to show how important is method inlining. The dark blue graph, the dark blue line that you see is basically if you did not do any method inlining. On the y-axis is speed up normalized to the default inliner. So if you didn't do any inlining, you got 60% of the performance, so you had a 40% performance drop. Or the other line that is shown is just random inlining decisions. What if you just had a coin toss for a random inliner? What we see here is that a lot of times you did not do as good as the default inliner. In fact, only 0.2% of the time, 0.02% of the times when you actually got a speed up, and that basically means that the default inliner was actually very, very good. So it's basically looking at a needle in a haystack, and it's not a low-hanging fruit, and method inlining is important. So let's look at the stack size of the haystack. If we just look at one particular benchmark, the Spec JVB 2005 benchmark, just one run of that had 1,250 inlining decisions that needed to be made. Each of the inlining decisions can impact all the other future inlining decisions. So you have a sample space of around 2 to the power of 1,250 possible solutions, and it would take a very, very long time for you to actually go through each solution to come up with the best one. Now that is just for one application. If you have another application, you start all over again, and that is the hardest problem that Devi has seen in a long time. So what are the different factors that could affect inlining? Simple factors that you can think of are the size of the collar, the size of the collie. What are the percentage of branch operations, the number of memory operations? So if you've got more memory operations, that means you've got bigger advantages in doing instruction scheduling and things like that. What are the other method calls? So if you've got more method calls, that means that the present inline decision might not be as important as all the future ones that you're surely going to see later on. Or whether the call is in a loop. If the call is in a loop, by default, you could assume that it's going to be used multiple times. So you get all the advantages, but you pay for it only once. So these are the different factors that could affect it. We don't know how they would actually affect it, and that's why we wanted to do machine learning to figure out what to do. So let's take a brief look at what the present inlining mechanism is. We did our work on Maxine VM and the hotspot VM. I'll show you what the hotspot VM does. Hotspot VM just does some basic sanity checks whether you would break anything if you inline it. If you do, then you don't do it. Otherwise, what it checks is whether the collie is less than the trivial size, means you get all the advantages, and it does not increase the size of your parent method, so you just inline it. You've got no cost associated with it. The other one is, if it is bigger than the trivial size, what you do is you check whether the collar size is less than the maximum allowed. So if the collar is already really bloated, you don't want to inline it. Other than that, if it is not too big, what you do is you check the inlining level. If the inlining level is too deep, you don't do it. Or you check whether the call is actually warm or not. If it is not warm, if the answer to any of these questions is a no, you don't inline. If the answer to all of them is a yes, you inline. Now, this might look simple, but the problem here is that there are a lot of corner cases and there are a lot of what ifs. For example, what if your callee size is small, the caller size is average, but there are a lot of other method calls. So you might be betting on inlining that particular method call, whereas something else in the future is going to be more important. So how do you take care of that? Even if that is not the case, if there was no other method calls, the present method call is in an error handling scenario. In that case, again, you're going to inline something which is never going to be used, so that's also going to be a bad scenario for you. So the problem is that there are a lot of corner cases which the compiler writer cannot come up with when he's writing the compiler. So that is a big problem with a static heuristic. Another thing is each source code, each application is different, and each one might want to be treated in a different manner. So for example, in this particular graph, if you look on the y-axis, again, is the speed up normalized over the default inliner. On the x-axis is the max caller size. And if you look at all the different values here, what we tried to do was we tried to find the best threshold for the caller size and say, okay, at this point is where I create a cutoff and say any bigger caller sizes, I don't inline. Now, if you look at this graph carefully, you realize that at this point, all these are at the maximum, but the Java C benchmark went down. So Java C might perform better if it had a different max caller size threshold. So each application potentially needs to be handled in a separate way. So there are different possible solutions, and we'll look at some of those. Previous solutions were just doing random sampling. Random sampling is do lots of random thresholds and figure out which is the best threshold to use. Another was genetic algorithms, which was a much nicer improvement over random sampling, where you could go through a lot of search space and it'll be a lot faster than doing random sampling. But what we're proposing is neural networks and decision trees. It is not really possible directly to use decision trees, but I will go into that in the later slides. So the disadvantages of the previous solutions. One is the heuristic is primitive. That by no means is a fact. I'm not saying that the inlining heuristic right now is bad. I'm just saying that whatever is a heuristic that is written into the compiler by a human being is all that it can do. The only thing that you can play with are thresholds. So if your thresholds aren't really good, your inliner is not going to be very good. And the other part is that it is non-adaptive. It does not take into account the system itself or what other system needs. If the system is running low in memory, you want to be conservative and not inline, when other times you might want to inline. And in case you want to change the inliner, again, you have to go to the compiler writer and say, I need a new inliner. And he would sit down and try to do the same thing again, and that's the next heuristic that you would have forever. So what our proposed solution was to use machine learning, which would give you a better solution or give you a better heuristic to tune the inliner. What we did was we added neural networks into the hotspot VM. So in this particular case, what happens usually is you load the bytecode. When the bytecode is loaded, during the load process, we just generate features. Features are basically static source code features, which would give you a rough idea of what this source code is like. Those features were given to the neural network, and the neural network would make a decision of whether to inline or not based on those inputs. Once the decision was made, it was given to the JIT compilation, where it would compile it, run the piece of code, and we would calculate the speed up, comparing it to our baseline, which was the default inliner. Once we calculated the speed up, we would use that as a feedback to the neural network. So the neural network would be good if it did faster than the baseline. It would be bad if it did worse than the baseline. So that's roughly how we modify the hotspot VM and use the NEAT, which is an evolutionary approach to neural networks, to generate the neural network. So a neural network in its most basic form is just a directed graph where you've got inputs. All the green nodes are inputs, and once you activate those nodes and you propagate those values, in our particular case, you get just one single output. The single output is simple: above 0.5, you inline; below 0.5, you don't inline. What are the inputs that we use? So the inputs that we used were basically a combination of source features and profile information. Source features, we had 8 of them which were based on the callee, 8 of them based on the caller, and there was some profiling information like branch prediction, invocation counts, and things like that. One single output that was there was whether to inline or not to inline. It's a simple question, to be or not to be. So using NEAT. NEAT is basically a genetic algorithm. NEAT is like a genetic evolutionary approach to doing neural networks. So what it does is it starts with 50 random neural networks. Once the neural networks are generated, you evaluate each neural network and figure out which is the best neural network. Once you have the best set of neural networks, you say, okay, these are my best neural networks. I will take those and go propagate them to the next generation. And you use those to populate the whole generation, and so on. That generation would have its own best neural network, best performing neural networks. You do this over multiple generations, and in the final generation, you would have this one good neural network. At least I used to hope I would get one really nice neural network which would solve the problem. And each of these dots that you see is a separate neural network in itself. So if you look at a training run, we have this here. On the x-axis are different generations. So we went through over 300 generations. So each generation is 15 neural networks. So that's like 6,000 neural networks and 6,000 evaluations of all the benchmarks that were there in the training set. So that's a lot of computation. And as you can see, over multiple generations, you had an increase in performance. So because it was computationally very intensive, we tried to do some kind of a distributed system where the master node would just generate neural networks. Those neural networks would be given to the slaves, and they would run the benchmarks, come back with the right speed up. And once you had the speed up, all they needed to do is tell the master, the neural network that you gave me is good or bad, or how good or how bad. And then the master would generate the next set of neural networks. So that really improved or increased the number of generations that we could go through. Otherwise, it would take forever to do one single evolutionary run. So the problem with ANNs or artificial neural networks are that they don't provide any intuition. As in, you just look at the graph, you're not going to understand what it is doing, and you don't really want that. But the other problem is more subtle, that it cannot be debugged, and that is a bigger problem with compiler writers. If you can't have something that is debugged, if you don't know how to predict what it is going to do, nobody wants to write that into a compiler, which is a pretty big problem. So if we could get a decision tree, it would be an answer to both those problems. A decision tree would give you an intuition, and as well as the fact that it can be debugged, you would know exactly how the decision tree was reached. Unfortunately, the problem was you can't create a decision tree without a labeled dataset. A labeled dataset is basically, you need to know in advance what is the right decision to make at each decision point. If you don't have the right decision, you don't have a dataset, and if you don't have a dataset, you can't create a decision tree. So all we needed to do was create one. So in order to create a labeled dataset, what we did was the neural network that we had, we just considered that as our oracle. We embedded that into the VM, and what we did was at each decision point, we just looked at what inputs were given to the neural network and what output the neural network gave. So it was basically treated like the oracle, and each decision point was taken. We would take all the inputs from it, take all the outputs, and store that in a file, and then use that as our label data set. Once we have a data set, generating a decision tree is very, very easy. You just have to go through a C4.5. What we use was a C4.5 algorithm to make the decision tree. So the decision tree looked like this. So the best part about this decision tree was just looking at it, you would know what is an important factor, what is not an important factor. So one thing that we predicted initially was the block weight, which is based on the profiling information, which is how often is that block predicted to be run. And that was the most important parameter to be used. The other parameters that were important were how many method calls were there, how big was the size, and were there nested loops and things like that. So looking at the decision tree, we could reassure ourselves that the neural network wasn't really doing anything really crazy. It did make sense. So that was a welcome advantage to it. So let's look at this particular code. I can see, you probably can't see much, but basically this code represents the fact that you have a switch statement with multiple method calls, and then you have an if, which is empty, and an else, which has lots of stuff. So the method that we're going to look at, the method inlining decision that we want to look at, is this particular method call. So let's look at what the decision tree does. So this is our decision tree, and at that method inlining point, we see that the if we look at it, the if statement is empty. So any method, any control that goes into this particular method is going to go into that else statement. So that means our block weight was 1. So we know right off the bat that that method call is going to happen. So that's important. So we go to the right side of the tree. At the right side of the tree, we see, are there other method calls? Yes, there are method calls, but they're not a lot. So it's a smaller number. So you go to the right side and say, are there other stack operations? So if there are a lot of stack operations, you would not often inline, but you go to the right side again, and then we ask, does the callee have nested loops? So the callee has no nested loops. If the callee had nested loops, you would have gone to the right side, but now we go on to the left side, and we ask, what is the present size of my graph, or the caller method? The caller method is fairly large. Then you ask, if the caller size is fairly large, you ask, what are the number of memory operations? And because the memory operations were large, we decided to actually inline it, which basically means that you went through a process of figuring out what is important and what is not important based on all the past decisions that you had made. And this is how we came up to the inlining decision of inlining it. So let's look at the results. We used Maxine Research VM and the Hotspot VM. In the Maxine VM, this is the graph which is there in the paper. I can imagine you can't read it right now, so I'll just concentrate it for you. We had the average, we had the Capo benchmarks and Spec 2008 benchmarks which were used, and what we see is genetic algorithms, which is the previous state of the art for tuning a method inline, is in the blue graph, the blue bar, which does do well. It still gives you an improvement, but using the neural network or the decision tree would have given you a better performance of that application. Another thing that we can see is the fact that a process of changing the neural network to the decision tree did not affect the performance too much. So you got a lot of advantages of the decision tree being easier to read and easier to debug, and you didn't really lose a lot of performance while you were changing that process. So that was another welcome result, because this wasn't done previously. So the other thing that we wanted to look at were different source features and figure out what source features did how well. So this we did on the hotspot VM. This is the result on the DeCapo benchmark. So what we see is the blue bar is the original features. So original features are the features that were being used before we added all the new source features and source analysis. From that, using the same methods that we used previously, we got a 2% improvement, which is probably around the noise threshold. If we added new source features to this particular set of features, we got a 5% improvement. But the best improvement, we got a much better improvement if we had source, the profiling information also available to us, which gave us a 10% improvement. Now, this was just on a basic Java benchmark. Another interesting thing that we found was Christian Weimer told me that you've got Scala benchmarks which generate bytecode, and those bytecodes look nothing like the normal bytecode that is generated by a normal Java program. What happens is your application or is your process robust enough to actually go through it? The best part was that it was not only robust enough, but it actually improved on the performance. So what it basically means is that the hotspot was really, really highly tuned, but it was tuned for Java programs. But if you threw in something which looked completely different from what it was used to seeing, it didn't do as well. But our application, the neural network and the decision trees did fairly well, and you got an average of 20% improvement, which was pretty good. The last result slide is on spec JBB. Now, this is different from the previous ones because the training set and the test set was the same. We did this because these are one run of the spec JBB benchmark takes a long period of time, so we couldn't really add it to any of the training set. And the other part was the hotspot compiler writers said that they only care about performance on spec JBB, so they only tune their hotspot on this particular benchmark, and even sub 1% improvements on the performance was something that they would be very happy with. And just using neural networks, we realized, the source features and the profiling information, we realized that we could get pretty good speed-ups between around 4 to 8%, which was nice. For the conclusion, basically we had a few conclusions that you can outperform the best tuned system. We're not saying that our particular system is the perfect solution, but what I'm saying is just looking more into it, you would find better areas where it can be improved. Decision trees do provide a better insight to the inlining process, and source analysis is crucial in getting a customized solution which would be useful for getting a good final solution. And profiling information, of course, gives you a clear boost when you can get it with minimal cost. So that's about it. And,
let's thank the speaker. And we have a few minutes for questions. So let me start. So it's really nice to have decision trees so we can start to reason about when we're using these machine learning algorithms, why it's making the decisions that it makes. So I have a question. Are these decision trees portable across various architectures?
Good question. Exactly the question that the viewers had. I would want to say yes, but they're just as portable as the default heuristic that came with the compiler. As in, if you had the right training set and if you did the right training, they would be portable, but we didn't precisely account for architectural changes and multiple machines to do it.
And so you have, and in your experimentation, you had one decision tree, right, that you used across all of the applications.
Yes. Yes.
Okay. So, yeah. So that's good. And was there any, so beyond having this decision tree, were there any insights that you gained about just general, general decisions that you might want to make given one of the bubbles, right? If you have, right?
Yeah, so that was one thing that I really liked about the decision trees, is the fact that each of those bubbles, or a combination of bubbles, gives you a rough estimate of, okay, if this happens, this is more important, and if that happens, this is more important, and this is no longer important. Or if this and this happens, you might want to check back and look whether this is a different refined situation or not. So yes, however, you can't count on it. This decision tree, you have to remember, was automatically generated, and the goal is not intuition. It's just nice that you can generate some of the intuitions. You might just have another decision tree if you have a smaller training set, which would give you no intuition at all.
Hi, I had two questions. So the first one was for your spec GBV results. Was that using Hotspots VM?
Yes, the Hotspot server VM with the same set of flags that the Hotspot VM people use to publish the results on a similar machine.
And the second question is, for your baseline, does your decision tree end up actually just overall increasing inlining? And if it does your baseline maybe need to be an application, just inlining more at random? In the sense that, like, if your decision tree results in just more inlining in general, perhaps just more inlining in general is beneficial, and
right,
you could have done something in a random order, or did you constrain yourself to having the same method sizes?
We did not exactly do an experiment where we increase the general probability of inlining a decision. We didn't do that, but if I was to guess, I would say that just increasing the number of inlining decisions will not give you a performance improvement, because the minute your probability of inlining increases, you go through the whole graph, and more often the graph is going to be embedded into the parent method, and that is going to increase your, it'll bloat up the method fairly quickly. So,
right, but maybe that's not a bad thing.
I'll try it and find out and see, but I don't know.
Yeah, very good talk, thank you. I was wondering, with your experiments on Scala and like more, the impact of the kind of application or domain seems very interesting. So if you work, for example, in the Scala group, you would be interested in tuning the hotspot for Scala specifically, so not necessarily running the tuning on all the drugs. So is it something you could imagine that you could basically make it more programmable, these heuristics inside for given application domain? You basically train.
Yeah.
I mean, you can even program it. You may want to give some insights. I want these new features. I want these new important context information to be in the heuristic. Could you use your approach for that?
So at present, the way we change the hotspot, you have to manually change the compiler to add more features to it. But given that you want to improve on one particular application, you just give that as a training set and let it run and give you a good heuristic. So that will be hand-tuned for that particular application. So that part, you don't need any manual intervention in the compiler. But to add more features, we didn't really create a framework that could automatically add new source features, because we had a code which would actually generate source features by going through the bytecode. So if we can add more to that particular piece of code.
So we're using attributes or like annotations?
Yeah. Yeah.
All right, so we have time for the one last question, and we can have the new speaker start switching out. Do it.
It's lovely work and very exciting, and I hope to see it arrive in Hotspot very shortly.
I hope so too.
My question is, you've taken the neural networks, a big vector of numbers, and kind of squashed it down into the decision tree, and that did lose a little bit of the optimization. why not use your individual, because you made thousands of runs of each application with many different inlining decisions. If you record all those and use the one that has the highest performance for that application, then you'll actually have the labelled training set that you need to directly construct a decision tree. And that would seem to maybe give you a higher performance than the neural net, or at least the same.
Yes and no. One, because the run which gave the best performance also happened to be generated by that neural network. So the neural network generated those decisions, and the same decisions, exactly the same decisions were what we used and recorded. So yes, we used.
Yeah, I'm just saying for every single inline decision, record the best inline decision for that method.
So you can't really do that because you can't isolate one inlining decision of one method from all the other inlining decisions. So you have to have a holistic, like this one set of inlining decisions was all good, but you can't say one thing was good and the other thing wasn't.
Great decision. Let's thank the speaker again. And the next speaker we have for you is Boubacar Diouf, and he's from INRIA.